Okay. Okay. Good afternoon, everyone. It's a pleasure to have Professor Philippe Odier today with us today, giving us this GFL seminar. I think many of you may know about Philippe. Some of you may be seeing him for the first time. He is from the Department of Physics at the École Normale Supérieure de Lyon in France. He does laboratory experiments on rotating and stratified flows for his research these days. He is visiting us as part of a SPARK project on mixing and dispersal in geophysical flows. This is a project at IIT Madras. It's Professor Anubhav in applied mechanics, Professor Khanna in applied mechanics, and myself who are part of the team at IIT Madras. And Professor Philippe is an international collaborator on that SPARK project. He has visited us several times in the past. I think he will also visit us many times in the future. So, the floor is yours to listen to him on internal gravity waves and path to vertical mixing through laboratory experiments.
Thank you, Mani. So, hi everyone. Hi also people who are online, wherever you are. So, I'm going to tell you about linear and non-linear resonance of internal gravity waves, and is this a path to a vertical mixing? So, it's a work that has been the sum of the work of a number of students, PhD students, and postdocs. Here there are 7 of them. I'm going to speak mostly of the most recent results, of course, because that's kind of new, and these results are due to Julie, who was the latest PhD student. She defended her PhD in September. That's why her picture is a bit bigger, although it's pixelized, so it's not number. And I'm also going to show some old results, so old that his picture is black and white. From Baptiste Bourget, who was the first PhD student, he was a postdoc, the first PhD student on the project. And then, if I make the total, that this is 17 years of work. But don't worry, I'm not showing you 17 years of work. I'm going to highlight some interesting ideas and results. And this work, of course, has been done in collaboration with 2 colleagues, Sylvain Joubeau and Thierry Dauxois, who was still at BNS, although Thierry Dauxois is now a big shot at the CNRS, so he doesn't do research anymore. So that's it. So a few words of introduction, and maybe I'll go a little quick because that's kind of things I guess you guys know pretty well. Ocean circulation and mixing. This is a picture of the thermohaline circulation and the regions where you have production of dense water, of course, at high latitude because the water is more salty and colder, so it goes down. But if you want to have a circulation, as it says here, you have to bring the water back up, the heavy water back up. And so the hypothesis that was suggested by Monk and Wunsch in '66 already, even I wasn't born, it comes back up everywhere via turbulent diffusion. So if you agitate enough the water, you bring the heavy fluid up and the light fluid down, and you do mixing, and that participates in bringing the water back up so that you can actually have a steady state circulation. And so this is a conversion of turbulent kinetic energy into potential energy, bringing the heavy fluid up. And so if you quickly write some equations to the diffusion advection balance for the scalar, for density, with a decomposition known as the Reynolds decomposition, where you separate the mean values and turbulent fluctuations, you get for the equation for the mean quantity that there is a term, an additional term that is due to the fact that when you average product of 2 quantities, even if the average of these quantities is 0, the average of the product is not. And so that this quantity is called the buoyancy flux. It's actually how the fluctuations of velocity can move the density particles up and down, and thus create mixing. And so if you simplify the equation, you balance the principal terms, you get something like this. And then you have to, usually people in numerical simulation, to solve this equation, because you have to make a hypothesis on or an assumption on how to deal with this turbulent, buoyancy flux. So they make an assumption called the turbulent diffusivity assumption, where you write that this quantity is simply proportional to the gradient of density. So it's like what you have with real diffusion, molecular diffusion, that the diffusion of a quantity, the flux of a quantity is proportional to the gradient of the large-scale quantity. But this time it's turbulent, so there's a T in front of kappa. Kappa would be the molecular diffusion, but here diffusion is enhanced by turbulence. And so this quantity you expect it to be larger than the molecular diffusion. And so if you replace this into this equation, you get an equation like this, and you can write kappa T as W, which is the average velocity at which things are transported by this turbulent diffusion, times the ratio of the first to the second derivative of spatial derivative of density. And so if you try to estimate, people have tried to estimate this quantity from ocean data. So W you can estimate either locally by radiocarbon data or globally by making the balance of bottom water formation. And of course, this ratio, once you have the density profile in the ocean or a typical density profile in the ocean, you can compute this ratio. It has the dimension of a length because it's the derivative divided by the second derivative. And so that would give you a turbulent diffusivity. So this is about a centimeter per day. Oops, sorry. This is about a centimeter per day, this velocity, and this ratio here is about 1,000 meters. So you get 1 centimeter square per second. So which is larger than, for your information, the molecular diffusivity is of the order of 1 millimeter square per second. So you have a factor 4 between the two. And so now the question is this everywhere that I wrote here correct? Does it mean we have this 1 centimeter square per second turbulent diffusion everywhere in the ocean? Well, the answer is no. And there's one very famous paper by Paul Singh in 97, that's already almost 30 years ago, where he did measurements, actual measurement in the ocean of this quantity kappa T. And so the 1 centimeter square per second would be the value of 1, which is, this is also centimeter square per second, so it will be, let's say, yellow, orange will be 1. So clearly, in this region, it's much less, about 10 times less. And locally here, you have regions where it's actually 20 times more, because this is a log scale, some kind of log scale exists. So clearly, there are some turbulent mixing seems to be more localized than expected. The question is, what are the local mechanisms that create this mixing? So internal waves are a good candidate. Why? Well, they're likely to be generated near rough topography, and actually this plot, that's of course the interest of this plot, he superimposed to these measurements of kappa T the topography in the Brazil basin. And so it turns out that the topography is rather smooth here, while it's much rougher with lots of submarine mountains. And these submarine mountains are, of course, a good generator of internal waves, because you have tide that goes over and over these mountains, and these generate the waves. And these waves, as I'm going to show later, can be unstable, leading to small-scale secondary waves, which are more prone to induce irreversible mixing. So internal waves, well, very quickly, but you will know what they are, I guess. Yes?
So the measurement that is being made, will it always be done in the way you explained, that measure the vertical velocity, measure the density variation, and that is how you measure the...
That's a global estimate that was made by Wunsch at the time by using these sets of equations. But the measurement that was made by Ponzi was an actual local measurement, measuring the depth velocity gradients with probes locally in the ocean. Yeah. So an internal wave is a gravity wave in a continuously stratified fluid. So the mechanism is the same as waves at the surface of the ocean. So you take a particle of fluid, you bring it up, so it's in an environment that's less dense than the particle itself, and then you release it, and so it goes down, but it has some inertia, so it creates an oscillation, and this oscillation can propagate, and propagating an oscillation, that's a wave. So that's how you define an internal wave. So,
Can I ask?
yes.
From the previous slide?
Oh, previous slide. More.
Yes. From the picture, no, from the Poisson diffusivity picture.
Yeah. Almost. Yes.
There are slopes even in the regions to the left.
Yes.
Those slopes can also generate internal waves.
Yes.
Yes, they are shallower than the rough topography. But if it's barotropic tides acting over those slopes also can generate internal waves. So
I don't know. I would guess that you will have more where you have these spots, but here you're. I don't know. That would be my guess that you have lots of sources that you can relate to here. So if you send well, in fact, I don't know.
yes, it's a much more subcritical slope,
Yes,
but
yes.
it's still a slope.
Yeah.
That will also large scale internal waves it can generate.
Yeah.
But maybe what's important for mixing is smaller scale.
Clearly, I mean, smaller scale waves would be more important, and you guess we would have smaller scale waves here. We're really very large. So, where is that? So, this oscillation so there is a typical frequency associated with a density gradient, a continuous density gradient, which is called the Brent-Weisler frequency. So n is defined like this. So you have the density gradient times the gravity divided by the density. That's a square of a frequency. So the square root of it is the oscillation frequency. And then the dispersion relation is interesting because usually the dispersion relation of the wave relates its frequency to its wavelength. Here, the wavelength cancels out in this expression here, and what you're left with is only the orientation of the wave vector with respect to the vertical. So that's the interesting, so physically, in terms of an object to study for a physicist, it's quite interesting because it's a wave where actually the direction of the wave is related to the direction of propagation of the wave is related to the frequency. There are ubiquitous in the ocean. That's maybe not best picture because it's pixelized, but you can actually see internal waves even from above the sea surface. There are some events, the waves, of course, by definition, they are internal, they're not at the surface, but they have manifestations on the surface, and that can be seen from satellite images. I don't have time to explain why, but it's well known, and you see them everywhere in the ocean. So now to generate an internal wave in the lab, the idea is that, as I told you, in the ocean, you have one possibility is the wind on the surface, but the other possibility is to have the tide that's moving over a submarine mountain, and if you put yourself in the reference frame of the tide, you have this mountain that's moving. So in general, moving an object oscillating an object in a stratified fluid will create an internal wave. So what we did is that we designed a system, a wave generator, that is actually creating a moving band wave with a desired shape that will force the wave of the desired time. So this shape here is actually just a sine function of vertical. It's made with several plates that can move relatively to each other. So when you make it move, it's like this, it moves like this, and this will generate your internal wave in the ocean. We even, so that's a little distraction. I'm not going to talk about that, but I just wanted to show you the movie. It's cool. And that's actually the experiment that was done by Paco, one of the PhD students here from 2014 to 2017. And it was revived recently by Anouk, who spent 3 months with me in France and did some experiments on this. So you take your tank, you put it on the rotating platform. So the wave generator is here. It's placed at the top. It can be placed at the top or at the. So here, there's not enough water. It's not in contact with water, so you won't create wave. But of course, when you want to create wave, oh no, so sorry, I got the image wrong. The water level is here. So the generator is actually the bottom part of the generator is inside the water. Sorry, this is not the water. This is the laser plane that you use to make imaging, but your generator is here, and so you generate wave in here. So in this case, it's rotating, but I'm not going to talk about results with rotation. We also more recently worked on a wave generator that is axisymmetric instead of being linear. And the idea was that if you, for instance, have a storm that's agitating the surface of the ocean and that will generate these waves, it's more likely to be, on average, axisymmetric rather than having a linear wave. So we have this generator. Again, I'm not going to talk about it, but again, I'm showing the movie because it's kind of cool. When it's moving, it does this, so it's kind of course, you put this reverse, this you reverse it, and you put the moving surface at the surface of your water, and this screen allows to create an actual axisymmetric wave. So we need a bunch of studies also on this wave generator. Now, observing internal waves. So these are, again, you have the generator here at the top. It's generating the waves, and this is the processed image. So you see the propagation of the wave. So that's a nice feature. Well, nice. An interesting feature about these waves is that the group velocity, it's here, is in this direction. You can see the energy propagating. You have no waves, and then waves are more and more gaining space in this direction. So this is the direction where the energy propagates, so the group velocity. But if you take the phase is a given color. This color, you can go back again. This color propagates in this direction. So the phase velocity and the group velocity are perpendicular. That's a particularity of these waves. And what is more interesting is that they are actually inherently unstable. So if you keep playing this movie, after a few periods of the waves, or a few tens of periods of the wave, you start seeing a different pattern here, not the lines anymore, but something a little more complex. And this means that something different is happening, and instability is taking place, and your wave pattern is different. And so what is inside and what has been created here? So first thing you can do is do a Fourier transform to see if there are new frequencies that came up. And so one very useful tool that we use is this instability is called triadic resonant instability. I'm going to explain in a second why it's called like that. So this is what is called a time frequency diagram. So this is time and this is frequency. So it actually shows the time evolution of the frequency content of the signal or the image you're looking at. So this is our primary wave. So it's there from the beginning. It doesn't move. And these are two secondary waves that appear. So I told you a few tens of periods. So it's about 10 to 15 periods after the beginning after you start moving your generator. And so you have these two frequencies here, and if you make a cut at a given position to actually be able to measure the quantity, you have these three frequencies here. So this is the frequency, or actually the normalized frequency. Usually we normalize them by the value of the Brownian biseller frequency, so it's non-dimensionalized. This is the primary wave at 0.74. This is one of the secondary waves, and this the other one. And as it turns out, the sum of these two is equal to this, and that's a characteristic feature of this instability. That's why it's called a resonant instability, because there's a resonance condition between the frequencies of the different waves. Now, if you take your movie that we were looking at, and there is a signal processing process that has been developed in our lab, where we use the mathematical transform called the Hilbert transform that allows us to extract the frequency content or the spatial structure for each of the frequencies that are present in the system. So we saw that there were 3 frequencies present in the system. So by applying this transform, you get at the frequency of the primary wave, you get this, which of course looks exactly like the primary wave. It means that in this pattern here, part of it is just this primary wave. And then at the frequency omega 1, you get something that, as you can see, is different. The wavelength is smaller than here. The orientation has changed. And the second frequency, omega 2, you get this one, which is with a different wave vector. So this wave vector is in this direction, this one is in this direction. Of course, you cannot see it from a static image, but if you play the movie, this one is going like this, while this one is going like this, and this like this. And the interesting thing is that these 3 wave vectors, they also add up. So if you take them and you put them as a triangle, it actually closes the triangle, which means that there is a spatial resonance condition as well, in addition to the time resonance, the frequency resonance condition. So that's why, again, it's called triadic. Triadic because we have 3 waves, resonant, and stable. This study, this is where we stood when Baptiste finished his thesis, so in 2013, so it was a long time ago. But since then, we've done a number of things, and what I'm going to present now are results from Julie, as I told you, who was the last PhD student. And one of the things we decided to change, was that instead of having the wave generator doing this shape here, which creates a plane wave, what about the wave mode? So what is a wave mode? So we don't do this anymore. You can simply have a wall that moves back and forth like that. So to be actually precise, it's better if you have a sine function of like something that's moving, well, like the drawing here, like this and like this. But actually, even if you take just a flat wall and it oscillates back and forth, it will create a vertical mode. So a mode, in a way, it's the sum of a wave that's going in this direction and a wave that's going in this direction. So it will create something that will propagate, because you sum these two, it will propagate in this direction. And so you generate a vertical mode 1 wave. So I'm going to show you here. So these lines, the color lines that you see are the lines of isodensity, or high density, low density. And it's going to start moving. And you will see arrows as well, which are the arrows of the velocity field. So we measure both density and velocity field. So the wave is starting when you start seeing some motion, because you start seeing some white arrows. And once it has started, you see that this wave is actually currently, at that moment, it's made of vortices that are created from this moving plate and sent in this direction. And at the same time, you have your density isolines that move like a wave on the sea. But the thing is, at this end, it's closed. So the wave will reflect on this end and come back. And if there is not too much damping, the wave going in this direction and the wave going in this direction are going to sum. And if the conditions are perfect, you can get a stationary wave, which is what you have here. You see the voltages, they don't move anymore. They stay here and here, and you have a larger amplitude. That's what we saw at the end, very large amplitude of the wave. So this is actually what we call a mode. It's a mode in this direction that's forced from the beginning, and it's a mode in this direction, and that's forced because, so how do you force that? Well, you want total length of the tank to be an integer number of the half wavelength. So 1/2 wavelength, 2/2 wavelength, 3/2 wavelength. And so if you span through the possible frequencies and you look at the energy of the waves, you get this curve. So that's an experimental measurement. There's actually a more clever way to do that we discover afterwards. Because here you do one frequency after the other, you measure the wave amplitude and you get the energy and you get these plots, but that means that each of these dots is one experiment. But what you can do, especially if you have this oscillating plate, is that instead of oscillating at a given frequency, you do it at once, boom. And when you do that, you have all your frequencies, because that's the idea of a step function. It contains a lot of frequencies, not all frequencies, because there's of course a finite time for the plate to move. But it contains all the frequencies up to half 1 over the finite time of the plate to move. And so that's enough frequencies for you. Anyway, the wave frequency has to be below this grandfather frequency due to the dispersion relation. So you can actually do this curve at once. You get your signal and then you Fourier transform and you get this plot. So here we superimpose some theory. So if it's inviscid, you have something that tends to infinity because you have an infinite resonance at these resonant frequencies. So again, the resonant frequencies are when the wavelength, the length of the tank is an integer number of half wavelength. And if you add some dissipation, mainly sidewall dissipation, which is dominant in this case, more than bulk dissipation, this is coefficient that we computed that more or less takes into account sidewall dissipation, you get something that's pretty close to the experimental measurements. And now you can actually look at what the wave field look like in two different cases. This one, which is off resonance, and this one, which is close to resonance. And you get this. So when it's resonant, you get a higher amplitude. When it's non-resonant, as expected, you get a low amplitude. So the color here represents the W, the vertical velocity. So red color is going up, blue color is going down. So that's why it looks like this. And so in a way, we call these box resonance modes because this is a resonance, but it's just a linear resonance in contrast to the non-linear resonance of the TRI that I explained before. These are just box resonance in a box, and so you can have 1-1 mode, 2-1. So we decided to study mostly the 2-1 mode for various reasons. So what I'm going to show now, we focus on this 2-1 mode, which is actually the one you see here. This point here is close to the 2-1, and we studied various things that happen to this mode. So this mode happens to be itself unstable, just like the instability I showed you before with the plane waves. It also happens with these modes. So this red dot corresponds to this point here. So that's again is the time frequency diagram. You see the appearance of two new frequencies, which you do not see for the low amplitude case when you're off resonance. So this is a movie of what's happening to these waves quite some time after it has started. So it doesn't look as nice. You still recognize the mode with one color in the center and the two opposite colors here. But you can see several vortices, and that's due to the fact that you don't have only one wave, you have one modes, you have three modes. Because it turns out that, I'm going to show that in a second, these second waves, they are modes as well. So I come back to this slide just to, we can again apply this Hilbert transform and try to extract the structure of the waves, but this time we'll do it on this mode thing. So for the experiment that we saw that had these two secondary waves, well, that's if you apply your Hilbert transform on this wave, again you recover your primary wave. So with, remember, going up here and going down here, so that's the primary wave, the 2-1 mode. And then for one of the secondary waves, it looks like this. So this is a 1-2 mode. So how do you know that? Well, you go from light blue to intense blue, light blue again, then 0, and then light red, intense red, light red. So you have a one whole wavelength here. So it's two half wavelength. So the second number is 2 here. And here's the contrary. You go from intense red here to 0 intense blue. So that's only half a wavelength. Your red would extend all the way to here, and same for the blue. So this is only half a wavelength. So this is 1. Well, this one is a 2-1. This one is a 1-2. But you can count as I just did, or you can do what people call a modal decomposition. You project your structure here onto actual exact modes, and if you do that, you get, well, that's, in this case it's very easy, you get, so this is the result of the projection, and this is the different modes, M and L, and you clearly see that there is only one intense signal at 1, 2, so this corresponds to this 1, 2 mode here. Now the other secondary wave looks a little more complex. It looks like this, so you don't really, by eye, you cannot really say, oh, this is a mode 1 or mode 2 or 3 or 1, 1 or 2, 1 or whatever. So you can apply this decomposition, and when you apply the decomposition, you see that there are actually 2 modes instead of 1 here. That's why it looks a bit more complex. And these 2 modes are 1, 1 and 3, 3, because of course 1, 1 and 3, 3, they correspond, I'll show you in a second the equation that relates the resonance frequency to this L and M, and when you have L equal M, you can have any modes, 1, 1 and 3, 3 oscillate with the same frequency. So that's the frequency that we see here, and the 1, 1 looks like this, and 3, 3 looks like this. So that's again the results of the Hilbert transform applied to this wave field here. So, and what is interesting is that 2 minus 1 is equal to 1, and 3 minus 1 is equal to 2. So in a way, whether it's this one, and same for here, 2 minus 1 is equal to 1, 3 minus 1 is equal to 2. So, no, 2 here. So in a way, you also have your spatial resonance condition, except it can be a plus or a minus here. But whether it's this one or this one, it's resonant in space with this one and this one. So it is a triadic resonance stability, but for a mode and not for a plane wave. So it has a rich dynamics. So this is the one we've been studying since the last 5 slides. But there's another one that's we did another experiment with quite similar conditions, and this one has instability, and suddenly the secondary waves change their value, and you also get modes that are very different with the higher wave numbers here. And this is actually due to the sensitivity of, it's interesting, but you can never be exactly at resonance. You are some percent away from the resonance, and it turns out that it's very sensitive, because this is 0.07 away from the resonant frequency for the primary wave, and this one is 0.27 away from the present frequency, and you get completely different features here. Another characteristics of this rich dynamics is the influence of the tank geometry. The tank geometry, so it has a certain aspect ratio, and obviously you expect this aspect ratio to play a role, because that's what I told you about. If you write the dispersion relation in terms of the frequency related to the, so you assume it's a mode, your wave is a mode, and so you have an N and L wave numbers, then L and H, so the aspect ratio N over ratio L over H appears in here. So if you change L over H for a given M and L, for instance, you will have a different frequency, or for the same M and L, you will have the same M and L, you will have a different frequency, or for the same frequency, you will have different M and L. So clearly the tank geometry, which makes sense because if you change the tank geometry, you don't adjust the same number of half wavelength along the distance L. So that's the one we've been saying for some time now is is an aspect ratio of about 2, so it's twice as long as it is high. But if you take 3, aspect ratio of 3, this instability seems more stable in a way. You have your secondary waves stay unchanged for the whole duration of the experiment, while here you have a jump from 2 frequencies to 2 others. And if you make it shorter, 1:1 aspect ratio, then you get a very complex, more complex dynamics with lots of different secondary waves. So the nonlinear interaction scenario seems to depend on the tank geometry. So what we did to try to understand that, or at least to interpret, just one slide. And the reason it's so tricky is that this is actually an overdetermined problem. And so if you take your secondary waves, you can count how many parameters you have, how many unknowns. So you have 2 frequencies. Then you have 2 vertical wave numbers, and you have 2 horizontal wave numbers. Let's assume that the primary wave is given, and your question is, what's my space of parameters for the secondary waves? My space of parameters is of dimension 6. Now, what are the constraints? So the constraints are you want to have a triadic resonance condition. So one condition for frequency and 2 conditions in space. It's a 2D problem, so you only have two conditions. So that makes 3. Then you have the box resonance condition. Each of these numbers, M and L, for I equal 1 and 2, have to be integers. So that's 4 more conditions, because we have 2 numbers and 2 values of I. So we are at 7 already. And then you have the internal wave dispersion relation, which is the one I wrote before, except I took the square here instead of the square root, or the square here instead of square root. 2 conditions, because it's 1 for each wave. So in total, you have 9 constraints. So it's really an overdetermined problem. It is not possible to find a set of these 6 unknowns that will verify all these 9 conditions. Or it is possible, but you have to be lucky. So to try to understand this a little better, we did a weakly nonlinear analysis where, so if you write the equation of evolution of your integral wave in terms of stream function, it looks like this. So I won't go into details, but there's a linear part. There's a nonlinear part that with Jacobians that actually implies the wave-wave interactions in here. And then this is the dissipation part. This is the bulk dissipation, you have the viscosity here, and this is this term beta that takes into account the dissipation due to the wall friction, which is important in our case because our tank is not that big. So you try to solve this equation by taking a solution of this shape. So you have your mode here. So your mode is just a sine of pi over L and the sine of x over L and sine of mj z over h. So you inject that the shape of the mode already, and you assume that you're interested in the evolution equation of the amplitudes, and you assume that it's a slow evolving amplitude compared to the frequency of the wave. And when you do that, you get this equation here. Here there's an assumption that the amplitude of the primary wave is unchanged. You just study the evolution of amplitude of your two waves, A1 of the secondary waves. And so all these, here you have coefficients I, all these coefficients and everything here depends only on 6 variables, which are again H, L, the various M, well, the 6 variables that I mentioned before, of course, the M1, L1, M2, L2, and M0, of course, omega 0. So these coefficients are quite complex, but the expression is this one. And the interesting part of this study is this part here, because here we actually allow from a small departure from the dispersion relation. And this is because, again, since the problem is over-constrained, we have to give some flexibility. So we say, okay, maybe the frequencies of our secondary waves are not exactly the mode frequencies that we expect. So this part here, which is the imaginary part of this coefficient here, is related to the departure from the dispersion relation. When you do this, you get a growth rate. So that's calculates the growth rate of these instabilities. And as you can see, the bigger these terms, so these terms are these terms here, the bigger these terms, the lower the growth rate. So of course, you cannot depart too much from your dispersion relation, but you have to depart a little bit. And so we try to, once we get this, we try to compute in our cases for our different cases. So I'm back to these, as an example, these 3 cases that I showed you for 3 different aspect ratio. And so for this one, so what this plot here is number M1 and number L1. Well, of course, when you have M1 and L1, you have M2 and L2 by the resonance condition. And the color here shows the growth rate. When it's green, it's negative. So if it's negative, you have no instability. When it's brown, it's positive. And the more brown, the more positive it is. So here, and the color symbols here correspond to the actual measurements the actual waves that we measured. So these 2 here are the diamonds. And when it changes to these 2, they are the circles here. Forget about the process detail. So clearly, what we see, at least for these ones, the diamonds, they appear where they're supposed to appear, which means they appear at with the spacer structure, which gives the highest growth rate, at least for the low wave numbers. You have possibilities at higher wave numbers, but as usual, higher wave numbers are not always favored by you to discuss it. So that's for this one. Same for this one. This time you don't have very low wave numbers, so they take the first. So these 2 values, these 2 peaks that you see here, they correspond to the highest possible growth rate that we calculated with our model. And the last one here, where you have lots of things, where you see that the intensity is the same scale for the 3 of them. So the intensity of the ground is larger than here, so it means you have more possible couple of Lm that give you a positive wave number. So it makes sense that you see more solutions here of your equation. Now, sorry, oops, I'm going too far. So that's a result we published last fall in an article in Physical Review Fluids. If one of you was referring to this paper, thank you very much. Thank you for considering whether it was worth publishing. Now, I'll come back to my original question, which is, do internal wave generate mixing? So mixing means that we need the wave to break so that you can convert. I explained that.
So,
Sorry,
in
this.
the experiments, like when you have this instability happening and further harmonics being generated, why does it not like continue? Like why don't you keep getting smaller and smaller scales appearing in the problem? There's something limiting there.
Well, sometimes it does, and sometimes it does not. So I guess again it's a question of some. So there is this issue of the constraints. That means that of course you favor the modes that will get a high amplitude because they fit well in the box.
Right.
So if your higher amplitude modes don't fit in the box, that won't work. And I guess there's also an issue of viscosity, because you are in an experiment. Your viscosity is large compared to the the Reynolds number is not that large, so viscosity plays a role. And so if you go to smaller scales, which you get higher mode numbers. So that's actually a discussion we had earlier with Manny, and in one of these the first paper by Baptiste, we showed that the growth rate actually you get a maximum at low wave number, and then it goes down very quickly as you go to higher wave numbers. Where if you put parameters like the ocean, then your growth rate goes. You can get a wave number that is 100 times your initial wave number, which means your wavelength will be 100 times smaller. But that's because in the ocean you are in a much bigger size, so this doesn't play such a role.
So I was thinking in the terms of that you had this diagram of the integers and you were trying to classify the growth rates, right?
Yes.
You had M and L. So in some ways, if you were to push up the Reynolds number to get towards like a spectrum that gets automatically generated through this sequence of instabilities. That
Yes,
should be
well, that's
possible.
the idea of wave turbulence. I mean, if you go further on, that's a kind of feature. Yeah. So, mixing. Coming back to mixing. So, to actually observe mixing, well, I already showed you some movies, but what we do is that in addition to do PIV, which is you all know probably, it's the classical way to measure the velocity field, we also measure the density field using laser-induced fluorescence. So you use the same laser, but you inject some dye in the flow. It's a dye that gets excited at the wavelength of the laser that we use for the PIV, but it re-emits, because that's the definition of a fluorescent dye, it re-emits at a different wavelength. And so if you have two cameras, one with a green filter that only sees the green light that is re-emitted by the PIV particles, and one camera with a yellow filter that only sees the yellow light that is re-emitted by the dye, then you can both measure density and velocity, because the dye concentration is actually a proxy for the density, because you put the dye together with it. The heavier the fluid, the more dye, or the less dye, whatever. And this gives you a nice way of measuring. And you can measure both together at the same time simultaneously, so you can actually compute quantities like this famous rho prime W prime, the buoyancy flux. So if I keep playing the movie that I showed earlier, I stopped the movie more or less at this point when I played it a few slides ago. But if I keep playing it, you start seeing that you have your isolines very quickly get these features where they actually overturn. So it's like the wave at the Marian Beach here, where it goes like this and then overturns, and this is very likely to get mixing. And actually the velocity field with the arrows also gets more complex. That's why I showed you another movie earlier. That's because, of course, you also have your secondary internal waves that are generated here. So there is actually potential for mixing clearly here. So one thing is that we measure turbulent diffusivity. Since we measure rho and W, you can compute rho prime and W prime divided by the local gradient, and you get a measurement of turbulent diffusivity. So interestingly, in cases, so that's an old measurement, but in cases where there is no TRI, so your velocity field looks just like the ones I've showed you before for the mode, and you get actually nothing. So this is the field of turbulent diffusivity in millimeters squared per second. So one would be the molecular diffusion, but of course we don't go down to this resolution, but it's clearly compatible with 0 here. While here, in the case where you do have TRI, and you can see that the TRI appearing, so it's a mode that's slightly higher here, remember. So the TRI appears, there is a destabilization here of your wave structure. And here you see values of the turbulent diffusivity that go all the way to 10 or 20 millimeters square per second, so 10 or 20 times the molecular value. So clearly there is some KT, some turbulent diffusivity here. One thing is that actually here it says 26T0, so that's showing 6 periods of the wave, and this is about 4 minutes. But clearly, if you want to see mixing, it won't happen in 4 minutes. You have to wait longer. So we did studies where we actually studied the evolution of the profile. So the profile is initially linear, the density profile, and you can see that it becomes more vertical in the center. Vertical means that since this is Z and this is rho, it means that it becomes more and more homogeneous. If it's completely homogeneous, you would have a vertical profile because density would be constant. So the more vertical means more mixed, and you can actually compute the evolution of potential energy. So the potential energy is the integral of rho Gz dV divided by V. You can divide it by rho to get actually a quantity that is that's an energy per unit mass. So if you integrate rho 0, that's the potential energy you have initially. But if you compute rho, I should have put actually rho Z and T. So this one depends on time, but you subtract the background density. So this is actually the density anomaly with respect to the background density. So it's actually the additional potential energy that you added to your system by mixing. So it starts at 0 logically, because at t equals 0, this is equal to this. So again, I should have put this one dependent on t. And then it increases. So you have several plots here, but just focus on the actual background potential energy is this yellow one here. Forget about the others. So this yellow one, so it increases, and then there's a time where it seems to stop moving, and then stop evolving, and then it increases again. Well, this is the same experiment, but with small amplitude. This is factor 2. That's an amplitude 1 centimeter for the oscillating plate, and that's half a centimeter. And so, big difference here. If it's a small amplitude, you have a little bit of energy, but it doesn't increase really. And you still have TRI, but it's stable here. While here, interestingly, at the time where the mixing seems to stop, you also see that your 2 secondary waves are not present anymore. There is a kind of a transient time between here, and here you have again secondary waves, but at a different frequency, and it starts again mixing. And this, we clearly were able to understand what's happening. So there are 3 regimes, that's what I was saying. So TRI plus strong mixing, then no TRI, no mixing, and then modified TRI and moderate mixing. And so, before I go to the spatial structure, once you get your potential energy, or the increase of potential energy, you will compute the mixing efficiency. So you divide by the amount of energy that is input by your wave generator. And when we do that, we get a ratio of about 10%. So that means 10% of the energy that is input by the generator in the system goes into increasing the potential energy of the system. The other 90% goes into heat. And that corresponds to an evolution of about 3 hours here in this case of the evolution. Now, why do we have this several regimes in the evolution of the potential energy? Well, so this, I showed you the structure of the mode 2-1. So that's the structure where the color represents the W velocity. But actually, it's more easily to observe if you look at the horizontal velocity component. So that's the same wave field, but that's the W, that's U. So here, as I told you, it's going up and down, so red and blue. But if you look at U, here it's going to the left, to the right, and here to the right, to the left. So you have these colors, blue, red, red, blue, blue. So that's your U velocity component. This is at very early times, 20 T0. But if you let it evolve, that's what happens. Something happens here, and it looks very different after 1200 T0. And that makes sense. We just said that we were mixing in the center. So we actually plotted the profiles here. So that's plots I already showed you. Initially it's linear, but here it's doing like this, getting more steep, and then like this. So here you have a mixed region, and actually it's more easily seen if you plot this Brunt-Weiser frequency, because the Brunt-Weiser frequency is the square root of, to some constant, it's the square root of the density gradient. So it's more or less the slope of this. So it goes down, or one over the slope of this. It goes down here in this region. So you have a mixed region here, which means, of course, the wave is not propagating in a medium where the density profile is constant. It's propagating in a medium where the density profile does this, and then this, and this. So it cannot stay, it has to feel that, the wave. So, and we actually computed numerically, if you try to solve the equation for the wave, just for the primary wave, and no instability, but for the primary wave, in a profile that is not linear anymore, but it's like this, you actually get a structure that is like this. So the modified electrical structure of the velocity field is actually the response of the system to the change of stratification. And so that kind of explains that once your system has changed, your primary wave is like this instead of like this, well, somehow the secondary waves don't want to be there anymore. Actually, if you look at times, this is about 500, so 500 is here, so you haven't, well, that's 400, you haven't formed your new system yet. So it's kind of this period, this transient period here is the time that the system needs to form its new structure. And when you are here a little after 600, so that could be like here, now you have something that seems to have converged to a new system. And so you have the reappearance of the instability, but with different waves, because the initial primary wave has a different structure. If you look at the modes that correspond, yes, the spatial structure associated to these waves, it is different from the spatial structure here. And so that can explain that your mixing stops here because your instability has stopped, because it needs to adjust to the system, and then it starts again after that. Last things, and I'm going to stop about an hour. If you try to look more locally at the origin of the mixing events. So in some region you have shear, you have velocity in this direction here, and in this direction here. This is extracted from one of the movies I showed you. And so if you have shear, you can have Kelvin-Helmholtz instability, and this is of course prone to create mixing. And the criteria for the Kelvin-Helmholtz instability is using a number called the Richardson number, gradient Richardson number, which more or less compares the destabilizing here at the denominator, the destabilizing effect of shear to the stabilizing effect of stratification. So it has to be, there's a criterion that was derived by Miles and Howard in the 60s. It says that if this number has to be somewhere low in the flow, lower than 1/4, to actually have this instability. And so here is a plot of the field of Richardson number in our flow. So less than 1/4 means very dark. So you have dark patches here and there, which means that, so the blue, I don't know exactly where that's, I think it's curious, but you have clearly regions where this number is lower than a quarter, so you have regions of Kelvin-Helmholtz instability. But the other possibility is what we saw before, these regions where the lines do this and this and this, so this overturning effect. So that would be what you could call a static instability. You don't need the shear, you don't need motion, you just need, if you have heavy fluid on top of light fluid, it will somehow create a mixing. So here, clearly, so the gradient is normally, the density gradient is negative because density decreases with z, but locally you can have a positive density gradient. Well, that's what you have here. Change the sign here. This is the fluid. If you go vertically here, the fluid here is heavier than the fluid here. Oops, sorry, fluid here is heavier than the fluid here. So you have a negative ratio of these two. So that's the normal one, which should be negative. This one, if there is a possibility of static instability, this one is positive, so the ratio of the two is negative. So again, this is a field of this ratio dz over d0, and again, it has to be negative for something interesting to happen. So you have some streaks here of negative values in some in various places. But looking at the field is kind of, you see something that is difficult to quantify. So what we decided to do is actually to plot the PDFs of the instability, of the quantities that control the instability. So how often in our field do we find values of Richardson number lower than a quarter, or how often in a field do we find values of these ratio that is lower than 0? And that's what you, so for Richardson, that's what you have. So it's actually a PDF as a function of time, because we want to see how it evolves. So vertically, it's a PDF. So if the brighter the color, the higher the likelihood that the event happens at this value of Richardson. So the quarter, this is 0, and so you should have nothing below 0 because, well, this could be negative, but positive, sorry, but if you take the average gradient, which is what we do, so it's always positive, but if it's below a quarter, it means your shear is strong enough that you can have Kelvin-Helmholtz. So that's the case of low amplitude, where we have very little mixing, and clearly there are very few events below 0. And this is the case at high amplitude, where we had this plot here, and clearly, and this corresponds to the times that delimited these three regimes here. So at the first regime, there are clearly lots of events below a quarter. In the middle regime, they kind of disappear, which explains why we don't have mixing anymore. And here they reappear, but to a lesser extent than here. And if you do the same for this quantity, you look at the same kind of plot, so time and the PDF of dz or d0. Here, so if it's the standard value here is 1, it means that d0 is dz is equal to d0, so the gradient has not changed with respect to, compared to the gradient that you have initially when you had no waves. So it's very close to 1 all the time, so you don't have any reversal of your isolines, isopycnals. Here, it's slightly different. It's still, you don't have many events below 0, except, interestingly, in this part, this last part. So it seems that in this second part, so you have to zoom in a bit, but you see some events below 0 that you didn't have before. So it's like the first regime was more dominated by Kelvin-Helmholtz instability, and the second regime, after the reorganization of the field structure, is dominated by the static instability. Okay, so I think finished. We submitted another article, this time it's submitted, so you are referring to this article. You can with us. Just submitted it 2 weeks ago. And this is some remarks of conclusion.
Any questions? Yes.
The time, the duration, you have no mixing. Is that it's a repeatable process? Experiments.
That's a good question, and I don't know because we wanted to do so many experiments with different parameters that I don't think we did twice the same experiment to see. You mean this time?
Yeah.
Yeah, I couldn't tell you. I'm not sure. It was really because she's the one, of course, who had her hands on the experiments, but I don't seem to remember that we really repeated exactly the same experiment. Sorry, I would not expect the time to be exactly the same because again, I mean, it's a calculated system and things can happen here, but they can happen later. Sorry.
So the first wavelength analysis plot that you showed, the frequency versus time plot.
Yes.
The secondary modes over there appear to die off towards the end. So why is that?
So in which, at the very beginning of the talk,
Yes.
I can go back to the slide, that's be easier, but I will do it like this. So you mean, yeah, I see what you mean. I think this one. You meaning this?
Yeah.
That's a very good question. And I must say that I have no idea. This was done more than 10 years ago. So it might be, no, I was about to say something. It might be that again there is an evolution in the system that because it also seemed to drift a little bit. If you actually the value of the frequencies seem to have changed. This you still have the sum of them is still equal to this because that's the constraint here, but they seem to go a little further apart, and then they seem to come back. So there might be something happening at that time. So that's, but it's shorter time compared to the very long experiments that we did later, because that's only 150 periods. And
would it have something to do with the window you used for getting this spectra? As it was the data?
that could be as well. Clearly, this is due to the window. This here with the reminder. So that's a good point. It could be just an artificial result of the sector.
Because on these kind of plots, you can also plot the mode of influence that tells you how much significant the signal is. So generally on these plots, the wavelet analysis plots, you get a mode of influence line. Anything that falls outside the mode of influence is not statistically significant. So if you plot that, those areas will generally fall on the other side.
Yes.
It won't be statistically significant.
Any other questions? I had a couple of questions. You've got a mixing efficiency in one of your slides.
Yes. I can.
Maybe we should ask if there are any questions from the online participants. Who's there?
Me. Oops, I'm too far.
Abhinav?
I think I guessed the question you may ask, but go ahead.
No, are you assuming the wave generator to be 100% efficient? Because you said this means that 10% of the energy of the wave generator is going into mixing.
Yeah, so this might be 10% of the energy. So it's no, it's 10% of the energy that is in the wave initially. Because as you notice, if you want to compute the provided energy, normally the expression is this one, but you don't have the pressure. But there are some ways to actually overcome this difficulty and get the energy only from velocity. But I would say that this is actually the energy of the waves that is created, and not the energy you put by the generator. So the efficiency of the generator, I would say, is not going to be a very
So the provided energy is calculated from the data.
Yes, yes, from the data. Yes.
And next question is you talked about these mixing events.
Yes.
And understand you talked about two different kinds of. So are you assuming that this rejection number less than 1/4 for static instability scenarios? Are you assuming they cause intense mixing or do they cause?
Yes.
It is known that they cause mixing of a certain level. Why are you even calling them mixing events?
Because if you generate a Kelvin-Helmholtz instability, you create shear at small scale that is likely to provide events.
Yes, but you can say the same about TRI also. If TRI happens, you produce.
Yes,
Is there evidence that Kelvin
No,
Helmholtz
the
instability
TRI can be responsible for the shear or for. Let's go to this slide. So for me, the TRI, if you superimpose two waves, you can have in some regions very steep density isolines because the superposition of the two waves is resonant in this way that the two waves contribute to make your isoline more vertical. So I'm saying that if there's TRI, you're more likely to get this. And probably the same here because if locally your the shear that in a way you have shear by definition, an internal wave is only shear, right? Because your particle, if your velocity is doing, the particles are doing this, and so if by superimposing several waves locally you increase your shear, you will also decrease your resistance.
I understand that.
Yes.
I understand that it may also generate exact these instabilities, but I don't understand why they are called mixing events. How do you know that will result in mixing?
I don't know that they will result in mixing, but they are favorable to mixing. Both Kelvin-Helmholtz instability or overturns are both events that might lead to mixing with respect to your wave. I mean, if you look at your wave initially, the movie that I showed you here, first movie, this one. So if you look at you look at your movie, so I have to do this. Wait, I have to do this to be able to move in the movie. I want to go directly up here. Ah, I clicked on the wrong. Again here and somewhere here. If your wave is nice and no secondary wave and all that, you will never have events where you have a steep enough slope that it will overturn, and you will not have enough shear to create a Kelvin-Helmholtz. So in a way, the fact that by the structure of the wave you get events, localized events where either you get Kelvin-Helmholtz instability or you get overturns, that is prone to produce mixing. I'm not saying it will, but it's a necessary condition for mixing. That's the reason. I should call them necessary events for mixing instead of mixing events.
Is there the literature says something about the mixing efficiency associated with static instability or Kelvin-Helmholtz instability? Are there
This I no.
any other questions? Okay, if there are no other questions, we'll thank Philippe again.